Hello.
Is that the right code or?
It is, yes.
Hello.
Good morning. I don't care. Wow. Why is it so far away?
I had a question about we had a question about the lab. So for our for lab 6, our graphs were logarithmically fit. I didn't know if we had to inverse it or
No, you're just trying to apply what we did in class, right? So you've got the two variables that you're comparing to each other. You're trying to determine whether or not there's a relationship, a correlation between them. So you're not trying to fit a line to the data, right? You want to use just a linear best fit line.
So just slap a linear fit
Correct. Because what you really want is the value for R squared.
Okay.
Right.
And for the test, can we go over the first multiple choice? Because I can't find the right answer back.
For which, the last one?
Some
Well, we've got 4 minutes right now.
of it.
Let's see what I can do if I don't have it memorized. Here. Hi, Anna. All right. Oh, that's the kind of the food web, or food chain kind of question. With the cadmium?
Yes.
So this is an example of a top-down trophic cascade because cadmium is specifically causing the steelhead trout. It's harming, negatively affecting the steelhead trout. So which is the most likely immediate effect of an increase in runoff containing cadmium on the trophic structure of other communities. So you're looking at something that affects the highest trophic level, right? But then influences lower trophic levels. So let's see, there'd be fewer nymphs. Sorry, there'd be more nymphs because there's fewer trout. With more nymphs, there's fewer larvae, right? With fewer larvae, there's more green algae. Makes sense? There's just a change. We don't have to worry about any web. So the first option doesn't make sense because that's the population of green algae will decrease. There would be a large decrease in the trout population resulting in an increase in the damselfly nymphs. Well, that makes sense, right? Because if there's fewer steelhead trout, there would be more nymphs. So I'm going with option 2 so far. Increased stream volume, nothing in the question gets me there. Population of trout will decrease because the population of damselflies and nymphs, that's irrelevant because the cadmium that's entering the water is affecting the fish, not the nymphs. So it's option 2.
Okay, thank you.
Thank you.
The code is up on the board. Hope you can see it wherever you are. Welcome, everybody. Good afternoon, Nava. I'm glad you're here. Olivia, welcome. You're missing anybody. Oh, there's Spencer. Shay, not Trinklin. Nava, Bradley, Isaac. Olivia, Sophie, Nick, Zach, Toby. Okay. Let Isaac connect here, hopefully. All right, do we want to say hi to the people at home? 1, 2, 3. Hello! People at home, you want to say hi to the people here in the classroom?
Hello, how's it going? Imagine walking to school.
All right, we'll keep trying to establish a semblance of community across time and space. Welcome wherever you are. We'll start like we usually do with a quick check-in. When I created this one, I thought of once again all the change that we're experiencing in life, that it might be useful to take a moment to reflect on what's just been happening over the last few days to all of us. But really today is going to be about moving on from where we were and beginning to explore something new. We've been doing some work around feeding relationships and ecological relationships within a living system. So today it's going to be really our first 30,000 foot view, if you can allow me to use that descriptor, of, okay, great, so something eats something else, whatever those somethings are, how is energy being transferred between the organisms? Okay, heck, how is energy being transferred within an organism after something eats something else? Okay, so it's going to be a big picture view today, but over the course of this week, and of course it'll go into a little next week as well, my hope is that we'll have a chance to build a deeper understanding of how energy is actually transferred within a living system. Okay, so I have somebody yesterday called these pre-test questions. I guess we can call them pre-test questions, but I call them preview questions just to get a sense of what you know about energy transfer from physics and chemistry. But really they're just an opportunity to write what you know, to draw what you know, and then we'll circle back to one or all of those questions as part of the larger lesson today. And we will wrap everything up with a quick exit slip before you go. What questions do you have for me or for the good of the group before we begin? Drag the chat over here in case anybody wants to jump in. All right. Well, our check-in today, we've seen this one before, but I'd like to use it a little bit differently today. A lot of change is going on in our lives, and change is really the only true constant in life to begin with. So if you were to think back over your experience last week, wherever you were, whatever you were doing, could you drag the blue flag to the meme that you think best matches your emotional state last week? When you're ready, drag the star to the meme that matches or best represents how you're feeling right now. So before and after. If change is a constant, maybe we can actually visualize that change with this really simple check-in. All right, looks like things have stopped moving. So if I were to summarize what I'm seeing, there are, actually the blue flags were kind of scattered. Oh, people are moving again. It's okay. But there were quite a few blue flags, it looks like, at the koala at 2, that frisbee dog at 5, the, I don't know, the surprise dog at 6, maybe even the lethargic sea otter down below at 9. But the stars are much more clustered around 5 and 6. So I'm wondering, is anybody willing to share their experience over this past week, the before and the after, in terms of how you're feeling or how you felt? Not everybody at once. Your enthusiasm's overwhelming. Tired of talking about how I feel all the time. I get it. quiet group today. Let me just share a little bit as to why I keep doing this. I'm deeply concerned about your welfare right now. Okay. It's these little check-ins that give me a chance to see where you are. I've done a lot of personal work really on myself in the world of empathy. You know what that term means, but I was kind of late to the game. It's only over the last couple of years that I realized that empathy is feeling with somebody. Sympathy is feeling for somebody. I think a lot of human beings are really good at feeling for somebody. We're not always as gifted in respect to feeling with somebody. This is hard. This is hard. Whatever you're feeling is okay. This insight allows me to empathize with you because from empathy comes compassion. Compassion is the embodiment of empathy. I've heard some disturbing anecdotes over these last 2 days about there being lots of tests this week. Is that fair? Maybe projects too. Speak to debate tournament this week. And I'm not going to be that person who says, you're struggling, you're suffering, here's more. It's going to be the opposite. Here's less. Or here's more time to do what we were going to do. There's nothing more important than you as a human being, and you deserve to be treated as such. And if you're not, we as the adults are failing you. Now, does anybody want to share? Nothing in the chat either. Somebody asked me this morning, is there going to be a final exam for this class? Based on what I just said, could you answer that question for me before I answer it for you? Some of you are like, I really don't know. Maybe he's playing a big game on us. There will absolutely not be a final exam in this class this semester. Absolutely, positively not. At best, we'll get through 2 more take-home assessments before winter break. Probably 1, maybe 2. Let's say that. Definitely 1, probably 2. Okay? A final exam? Are you kidding me? In this time? No way. So, that came up this morning. I wanted to share it with you as well. Right? Okay. On to the biology. Okay. I'm hoping this image looks familiar. It's been a little while though. This is the Serengeti food web that had the wildebeest as part of it. We were using it a few days, what are days anymore? Class meetings ago. With the virus that caused rinderpest in the wildebeest. You might remember that. We were trying to use it as a way to think about top-down and bottom-up trophic cascades. We were pretty clear in terms of the virus not being a bottom-up influencer because it wasn't acting on what the wildebeest were eating. But it was hard to classify it as a top-down influencer because it wasn't really eating the wildebeest. But it was causing harm, right? Certainly made the wildebeest sick and they could die as a consequence. So we classified it more as a top-down, but not a clear top-down. So we have these feeding relationships, right? We have these ecological relationships. Other things are eating other things, but what we need to begin to explore is, okay, when something eats something else, if we know that energy is being transferred, how is that energy actually being transferred? Whether it's between organisms or within parts of the same organism, it's time to begin to explore that today, and really this week, albeit from a 30,000-foot perspective. Okay. You know what? You're right. I was playing a game before. There is going to be a final exam in this class. See this image? I'm thinking due date December 25th, maybe like 7:30 a.m. I'm going to need to redraw this image from memory. Colors need to match exactly. You're going to want a protractor to measure the angles for all those arrows. Make sure you have a ruler so that all those arrows are the right magnitude. And I don't know. What do you think? It's if we assign it 7:30, December 25th, have it due like 7:45, December 25th. So you get 15 minutes. All right. Close notes. No internet. And if you make a mistake, you're going to have to do the whole thing over again from scratch. Sarcasm, right? Some of you are still wondering, aren't you? Are you, like, honestly, are you still kind of wondering, is he serious? Is he serious? Is he serious? He's not serious. And yet your experience in other classes throughout your life indicate that I could be? That's sick, folks. That is sick and twisted. Some of you got it as soon as I said December 25th. Thank you very much. All right. So what we want to try to do today is begin to explore how energy moves through a living system. So what I've done is I've created 5 questions. So I'll give you control of the slides here in a little bit. And for each of these questions is either like a fill in the blank or circle a word or draw a picture. Some of this will be review, some of it will be new. So do the best that you can to answer the questions. There's a temptation of like writing a question mark or I don't know. Draw what you think the answer is. Because that way I can follow along and see what you're writing and drawing. And that will give me an indication of what you know already. Okay. But again, understand that we'll come back, we'll circle back, and we can go through any or all of these questions so that you develop a deeper understanding before you leave today. All right. I'd like to give you 10 minutes to do this, but I like to build in a break into those 10 minutes because I don't think it'll take you a full 10 minutes to answer them all. So whether you do it at the beginning, the middle, or the end, it doesn't matter to me, but please, 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 I implore you, stand up, stretch, mindful yawn, get a drink, go to the restroom. You don't have to just sit there for these next 10 minutes. Okay? All right, whoops, that's not what I want. Sorry. You have control of the slides. Okay, again, there's 5 questions. Write an answer, draw an answer, circle an answer to the best of your ability. If it helps, when you see the term exergonic, that term might be unfamiliar to you, but it might not be. What if you replace the word exergonic with exothermic? Would that help you to answer the question? The same for number 4. If I replace the word endergonic with endothermic, do you feel like you could answer the question that way? I love to see your thinking in real time. You're doing a great job. Some people went back to those energy box diagrams that you drew a lot in 9th grade to answer number 5. So if that's helpful, that might be a place to start. Yeah, you're definitely doing a good job. Don't forget about taking your break.
Thanks, the restroom.
Of course.
Thank you.
Come back together in about 5 minutes. minute before we come back together. If you haven't taken a break, something you might be interested in trying in the spirit of the break, just take the next 20 seconds and look at something 20 feet away. All right, folks at home, thumbs up if you're ready to move forward. Thank you, Anna. Thank you, Isaac, Olivia, Nava. All right, folks here in the building, you folks ready to move forward? Okay. Where would you like to start? Do you want to go through the questions one at a time? Is there one question that's calling to you? All of them? Okay. All right, we can do all of them. So I took you out of student mode. I'm going to move to the same questions, but to questions that have my notes associated with it. On slide 10. Hopefully you're there too. You know, if we're going to begin to think about energy transfer and things eating other things, what we're ultimately going to be looking at is metabolism. So when you hear the term metabolism, what comes to mind for you? Eating. Anything else other than eating?
Like how fast you process food.
Yeah, that's really common, right? How fast you process food, if you have a fast metabolism. Absolutely. But metabolism isn't just how fast you process food. So when we say process, that was Spencer who shared that, if you couldn't hear him. It's not just how quickly we break down food. So we're thinking about, for humans, right? Putting it in our mouths, chewing it, swallowing it, digesting it in our stomach, completing digesting whatever we've eaten in our small intestine, absorbing all of those nutrients into our bloodstream, right? It's not just breakdown, it's also build up. So there's two branches to metabolism. There's catabolism, which is the breakdown of the molecules that we're consuming. And with that breakdown comes a corresponding release of energy. But there's also the other branch, which is anabolism, which is the building, the synthesis of molecules. Heck, if that doesn't make you comfortable right now, then just think about it bigger picture. It's new bone, new muscle, new brain cells. Those are all anabolic processes. We're building things within our bodies. But anabolic processes require energy. So metabolism has two parts, catabolism and anabolism. Where are we going with all of this? Well, ultimately, it's the energy that comes out of catabolic processes that is directed towards anabolic processes. And the how of that is a big, big takeaway for this week. Okay. What questions is that bringing up for you so far? So thinking about that diagram again, it's important to note that every living thing performs metabolism. Okay. So it doesn't matter if you're a single-celled bacterium or a multicellular wildebeest. Okay. But if we start at the level of the producers, our plants, our autotrophs, our photosynthesizers, right? They're predominantly performing anabolic processes. They're predominantly performing photosynthesis. Right? They're building sugars from carbon dioxide and water in the presence of light. But we have to be super, super mindful here. That doesn't mean they don't perform catabolism. Because whatever they make, they're going to have to break down and extract energy from. So producers, plants, photosynthesizers, autotrophs, they're performing metabolism, just like the consumers do. Okay? The consumers, preferentially, right, are catabolic organisms. They're going to eat something, they're going to break it down, they're going to extract energy from whatever it is they've eaten. But that energy is going to be directed towards anabolic processes to make more of themselves. So please, please, please don't ever get caught in the trap of, well, plants make their own food and that's all there is to it. Great, they make their own food, but they have to break down their own food too. All right, second question. This is a really big difference between chemistry and biology, okay? An exergonic reaction, I gave you kind of a hint there a few minutes ago. An exergonic reaction can be thought of as an exothermic reaction, right? But exothermic reactions deal with the transfer of heat energy. Exergonic reactions certainly deal with the transfer of heat as well, but specifically deal with the transfer of free energy, the energy that's available to do work. Why is that important to biologists? Well, simply put, thermal energy, heat energy, can't do work in a living system. Right? And we know this. It's getting cold at night, right? Putting a blanket on when you go to bed. A blanket isn't giving you heat. I hope you know that. And don't you dare go down that, well, I have an electric blanket. Shut it. Put a blanket on, not because the blanket provides heat, but because it traps the thermal energy, which is constantly escaping from your body. It's a waste product. It's not being used by you. Okay? We're going to circle back to that in a second and why that's important to living systems as well. So if the thermal energy isn't being used to do work with inside of you or inside of any living system, what exergonic reactions are specifically targeting is the energy that is available to do something inside the living system. So I looked at your diagrams, and most of you drew something like what's on the screen right now. You had a spot for your reactants, right, that had more energy than the products did. You had your little hump, your activation energy hump, and of course, we still need to add energy into the system to energize those reactant molecules in a way that they reach that activation energy threshold, the reaction can take place, the products form, and in the case of an exergonic reaction, the energy that's being released, that's energy that's available to do work for us as biologists within a living system. Not to say that thermal energy isn't going to be released as well. It is, but it's of no use to us as living things. Okay. So again, pausing. Questions, comments, curiosities? Is this helpful? Just for review, if nothing else? Okay. So when you get to the third question, maybe you're even seeing that these questions tell a story. So when you get to the third question, you're beginning to think about the laws of thermodynamics. And I bet in ninth grade, you focused a lot on the first law of thermodynamics, that energy can neither be created nor destroyed. You spend like a ton of time like keeping energy accounts. Energy lost always equals energy gained. Not familiar? Maybe you spent some time on the second order, but that probably showed up more in chemistry than in physics. The second law of thermodynamics, right, simply states that entropy, that disorder, is always increasing within the universe, in the surroundings, outside of the system. And lots of you circled increase. All right, wait a minute. So how does that apply to us as biologists? Well, as biologists, we can't violate the second law of thermodynamics, right? It's a law. It's an observable phenomenon. So what's important is we circle back to that idea that heat is always being released from us, from any living thing, as a waste product. That thermal energy that's escaping out into the surroundings is causing molecules, heck, air molecules, to move faster, their kinetic energy increases. As a consequence, they're going to bump into each other more often. And with those increased collisions come more spreading out of those molecules. The surroundings become more disordered as a result of that transfer of heat energy from the system out. Thermal energy transfer is occurring with every living thing at every single trophic level on planet Earth. That's important because as long as the surroundings disorder is increasing, the system can remain ordered. Because, I hate to tell you, you're a pretty ordered system as a living human being. You are not randomness. Okay? So this transfer of thermal energy is really important because it allows the surroundings to become more disordered while the system is allowed to remain ordered. All right. So let me bring it all together with questions 4 and 5. An endergonic reaction, if I replace the word endergonic with endothermic, okay? Remember, making that mental adjustment in your minds. Okay, endergonic, free energy transfer, energy available to do work, not the same as thermal energy because in a living system, heat can't do squat. All right, so in an endergonic reaction, is energy absorbed or released? Absorbed. So is it moving into the system or out of the system? In. And we can define the system however we like. It could be a part of a cell, it could be a cell, it could be tissue, not plants. It could be an organ system, an organism, a group of organisms, groups of organisms, an ecosystem, planet Earth, it doesn't matter. Don't you spend a ton of time in 9th grade also defining the system? I'll just do it too. So an endergonic process moves energy in. So our endergonic processes, here's that blank, anabolic or catabolic. Energy absorbed or energy released? Go back. No one's really writing anything down. So if I gave you control of the slides, is an endergonic process catabolic or anabolic? Say it again. Are you asking or telling? What do we know about anabolic processes? Do they absorb energy or do they release energy? Sorry? They absorb. So if an endergonic process moved energy into the system, is energy being absorbed or released? Absorbed. So one last time, is an endergonic process anabolic or catabolic? Anabolic. So those exergonic processes that release energy, here it comes. Terrible baseball player. Are exergonic processes catabolic or anabolic? Catabolic. Okay. So how does this all come together for us in just a few minutes that we have left? In that 5th question, you were asked to consider, all right, how is energy moving from an exergonic or a You could go down that way. We just did it though. An exergonic or a C word. Catabolic. Anybody who says your brains are all there right now at this time in life, I don't buy it. You guys seem tired, distracted, hard to focus. So, one more time. An exergonic process is catabolic. An endergonic process is anabolic. So how might the energy flow, move, be associated as energy is released from a catabolic process and makes its way into an anabolic process? Because both of those processes fit under the umbrella of metabolism. Well, as this week continues, we're going to be looking at a molecule that acts as that shuttle, as that energy transfer molecule. But I bet you already know what it is. That's a three-letter acronym. Hope you remember?
Is it ATP?
It is ATP. ATP is going to be responsible for transferring energy between exergonic processes and endergonic processes. Heck, sometimes ATP itself, the catabolism of ATP, is the exergonic process that energizes an anabolic process. We'll be looking at how that works later in the week. But as I looked at your diagrams, I saw a lot of pictures that looked just like mine. You had an exergonic diagram on one side, an endergonic diagram on the other side. What was missing, and that's okay, is how are the two connected? They're going to be connected by this molecule called ATP. So we will complete a much more inclusive diagram later on. All right. So I want to pause there, give people a chance to ask any questions that they might have. So I've been talking too much. Okay. I'll show you next time. For the sake of time, if I tried to draw it and show you all at the same time, I think the bell would ring. So take it out of student mode here for a second, because we only have a couple minutes left. You've heard a lot. I've talked a lot. You've done some work. One of my hopes is that when you look at the agenda slide each day, you're looking at those science ideas, those learning objectives for the day. You simply were to reflect over these last 30 minutes or so. What have you done? What have you seen? What have you heard that connects to one or more of those science ideas? Ooh, I love that. There is a constant input of energy due to a constant loss of energy. Beautiful. Yes, the second law, the requirements of the second law are met due to the transfer of energy. Yes, the surroundings must be unordered in order for a person to be ordered. Right. Well, as soon as you've added your reflection, folks at home, you're welcome to sign off. I'll see you in a couple days. Folks here in the building, you can pack up so I can spray off your surfaces. You come down. Very well.
Yeah.
Different